Okay. Thank you, everyone, for being here. I'm Aman Mehta, and I'm a graduate student at UCLA in Professor Pranay Narang's lab. And today, I'm going to talk about trying to simulate non-unitary evolution on unitary systems, which are by which I basically mean trying to simulate open quantum systems on our quantum computers. So just a quick refresher, what are open quantum systems? Open quantum systems basically, sorry, oh, yeah, see. Okay, so open quantum systems basically involve like the environmental degrees of freedom, decohering our closed system, and in principle, no real system is closed system, right? And so mathematically, open quantum systems are described by your Lindblad master equation, which I'm sure everyone here should be familiar with. But more generally, they can be described by Krauss operator sum representation. And this is basically the regime where we work with simulating open quantum systems. So how do we go on about simulating open quantum systems? As you can imagine, simulating any open system would require, in some way or form, emulating the environmental degrees of freedom on your system. And many algorithms on quantum computers, what is done is some sort of ancillary qubits are employed to embed this open system in a larger dimensional Hilbert space, often called dilation, to emulate the environmental degrees of freedom. And some of the strategies, this is not an exhaustive list, include like simulating the Lindbladian or Sinagi dilation, some sort of SVD decomposition, or some other form of unitary decomposition, and then encoding into quantum computers using maybe like LCU circuit or something like that. So one of the interesting methods that were proposed in PRL in 2021, I'm going to go over that briefly because our algorithm is kind of, in the same domain, is like comparative to that. What they do is, if you have any square matrix M, which is non-unitary, it can easily be decomposed into Hermitian and anti-Hermitian components. And then you can take a first-order approximation where you can use these Hermitian and anti-Hermitian as the generators to create unitary matrices. What that allows you to do is basically, up to first order, represent any matrix M as a sum of 4 unitaries with an error that scales at epsilon square. And these sum of unitaries can be implemented on an LCU, using LCU or some other form of encoding of unitaries. Now, some remarks, right? So this is a very simple scheme in a way which is an advantage, and it uses like log of four terms, so it uses 2 ancilla qubits if you're implementing it using LCU. It's a first order approximation, so the error scales with epsilon square. So for a good approximation, you would want as low of an epsilon as possible. But we also know that the variance of the output for LCU would scale as an L1 norm of the expansion would be like 1 over epsilon square. So what, in principle, that implies is to get a better accuracy, you need a higher amount of shots because you want your epsilon to be as low as possible. Here was kind of the inspiration for our method. What we would want to do is to find an exact decomposition that would reduce the mean square error and require less shots, and hopefully can be achieved with a minimal dilation. So the inspiration is from Sylvester-Lagrange interpolation, and this is not new. This is basically an equation from 1800s, which basically allows you to express any analytical function of a square matrix M as a matrix polynomial times the Frobenius coefficients, which are functions of the eigenvalues of the matrix. Now, if we take a page from the last paper and pick M to be either the Hermitian or the anti-Hermitian component and substitute function of matrix as the exponential, what we get is essentially we can express S and A as like exact decomposition of unitaries. And this is not an approximation, so we get rid of the approximation error. Analytically, what it would mean is that in blue you can see the first order approximation for the mean square error versus the number of shots, and in pink you can see like an exact decomposition, and you can see basically with the total number of shots you can achieve arbitrarily low error scaling asymptotically. So some remarks about this method then. We say that in the paper that this decomposition is not unique, and you don't necessarily have to use the Sylvester-Lagrange interpolation, but it can be satisfied by an infinite number of parameter vector mu. And if that's the case, the way you go on about calculating your coefficients of the expansion is using this sort of matrix equation. Further, we show that the L1 norm of this coefficient vector, C vector, is lower bounded by the maximum eigenvalue of the generator matrix. And for a Krauss map, the generator matrices S and A, it's known that the maximum eigenvalue is basically upper bounded by 1. So in a perfect case scenario, you can achieve an L1 norm of close to 1. Yeah, moving on, how do we find this coefficient vector? So we find that like exactly calculating these coefficient vectors is for higher dimensions is not exactly possible, at least to the extent we tried. But this can be framed as an optimization problem, classical optimization problem. So what we say is the parameter vector, an ideal parameter vector, is what minimizes the L1 norm of the coefficient with respect to these matrices, where E is the matrix you saw on the last page. And so there's a simple heuristic that we propose is that we notice in our simulations that the optimization is very sensitive to the initialization of the parameter vector. So we suggest the sampling of the initial parameter vector from a broad range for a subset of the problem, and finding the ideal range that suits best for the problem. And this process can be repeated for various different optimizers. And in our result, we see that SLSQP performs the best over like a randomly generated set of non-unitaries. More broadly, the structure of the problem will dictate the ideal range. So, coming to the results, on the left, right, you can see on the y-axis there is SQR, which is the solution quality ratio, and on x you can see the dimension. Here we are focusing on showing the scalability of the method in near-term regime. So solution quality is basically defined as the ratio of the L1 norm we achieve using the optimization versus the maximum eigenvalue. And as noted earlier, the best case scenario is the L1 norm should be equal to the maximum eigenvalue. So the best possible solution quality is 1. Now, this is for like a completely unoptimized the solution quality. If we use Kobila, for example, we see that we are able to achieve some sort of decent solution quality, but like I said, the SLSQP, you can definitely achieve definitely this is sub-exponential, but we have not set like an analytical bound on it, but we show numerically that a good solution quality can be achieved for up to 64 dimensions, and possibly higher too. And on the right, what we do is we use the scheme. Oops. Sorry about that. So what we do is we use the scheme to simulate a non-unitary channel, specifically the amplitude damping channel, and on this solid dotted lines, you can see the analytical results. The crosses are the simulation results on a IBM simulation device. And you see it's like follows closely. I haven't talked about how exactly we implement it, but we do go in details in our paper. But I would like to conclude with what we do is we find a method to decompose any matrix into sum of unitaries, and we can get it, compared to previous methods, we can get it scaling, basically measurement cost, improvement of 3 orders of magnitude, and using a stochastic implementation of the method, which you can follow in the linked paper. You only need like a single qubit dilation to implement it. So what's the trade-off here? The trade-off is basically there's a larger classical overhead. You need to basically do optimization, and the number of circuits increase because of the stochastic implementation. This gives us a method to implement it in near term, and we have ideas about using the exact decomposition into unitaries for other matrix functionals in the future. So with that, I'd like to conclude and acknowledge my group of the postdocs and graduate students and the professors I've worked with, my advisor, Professor Pranarang. This is the link to our paper. Thank you.